A rotating detonation engine is not useful just because it can detonate. It has to stay in the right combustion mode. This paper studies combustion mode transitions in a hydrogen-fueled, air-breathing, rotating detonation engine. The work is a direct connect experiment, not a flight demonstration, and it asks a practical control question. Why does one operating point become a stable, single rotating wave, while another becomes a collision wave, a hybrid pulsed rotating mode, or chaotic combustion? The paper's central answer is that two physical levers dominate the observed transitions in this tested setup. The first lever is local fuel-air mixing quality. When hydrogen was injected downstream in the expansion section, the experiment produced counterpropagating collision waves. In one key case, the clockwise and counterclockwise waves moved at about 1226 and 1031 meters per second. Those speeds were more than 30% below the ideal reference detonation speed for the mixture, so this was a highly non-ideal regime. When the injection position moved upstream to the combustor inlet, the local mixture improved. The engine then settled into a stable single-wave mode with a measured wave speed of about 1,613 meters per second. That is still not ideal detonation, but it is a much cleaner operating state than the collision wave case. The same theme appears in the partial premixing tests. In this tested setup, 30% premixing still produced collision wave behavior. About 40% premixing produced stable, single-wave behavior. But 50% premixing reached a backfire or failure limit. So the lesson is not that more premixing is always better. The lesson is that there is an operating window for useful mixture preparation. The paper also shows why inlet temperature matters. Raising the inlet total temperature to 1200 Kelvin changed the hydrogen jet penetration and degraded mixture uniformity. Under the tested conditions, that pushed the system back from stable single-wave operation toward collision wave behavior. The important point is local mixture quality, not only the global equivalence ratio. The second lever is coupling between combustion pressure and the intake. Moving the injection point farther upstream can increase mixing length, but it also allows pressure disturbances to interact more strongly with the isolator and intake flow. When this coupling was weaker, the experiment showed a hybrid pulsed rotating mode. That mode combined a 5.68 kHz rotating detonation component with a lower frequency 1.53 kHz longitudinal pulse. When the coupling was stronger, pressure disturbances disrupted the intake flow. That can starve the combustor of oxidizer, collapse the rotating wave, and drive irregular reinitiation. In the paper, this is the path toward chaotic combustion. The engineering takeaway is that rotating detonation engine mode control is a coupled injection, mixing, and intake stiffness problem. The paper provides experimental evidence and a measurement and control framework, but it is not a proof of flight readiness, and it is not a universal control law for every engine. For more engineering research breakdowns, visit www.ProReadyEngineer.com.